magnetization. So I know that these boards are kind of small, so I will make an effort to write big and to go slowly. If I go too fast, please do not hesitate to slow me down to give you the time to write down some things. Okay? So yesterday we had a sort of crash course in statistical mechanics, and I have explained you how we can have a thermodynamic description of a thermodynamic continuum description of a simple model, which is the Ising model of ferromagnetism. So I briefly recall what this was. It's a thin film of magnetic material. The magnetization can be in two states, upward and downward. And the model consists of a network of interacting spins. Okay? So a spin is a variable that can take two microscopic states up and down. And there is an interaction between the spins. And we have seen that this interaction gives rise to two phenomena, at least. The first is it gives rise to a phase transition. Namely, at high temperature, the system is disordered, meaning that half of the spin approximately are up and the other half are down. So that means that the net magnetization is around zero. Whereas at low temperatures, there is a breaking of symmetry, as we physicists call it, that is either the majority of the spins is up or the majority of the spins is down, which leads to a net upward or downward magnetization. Okay? And we have seen how you can describe this phase transition in a mean field language. That is an approximation in which, instead of taking into account all the correlations between the spins, you consider one single spin that is plunged in the field created by the other spins. Okay, so this gives a description of this transition between a state of zero magnetization and two states of non-zero magnetization. And we have seen how this can be described by a thermodynamic potential, the free energy, that has a single minimum above the critical temperature and a double minimum below the critical temperature. So that's the central description of the phase transition. And then the second thing that is generated by the interaction between these spins is when you go to a description of heterogeneous systems. Heterogeneous systems means systems in which the magnetization can vary from point to point in space, okay, which you need to describe something like domain patterns. So the central idea here that I introduced last time was coarse graining. That is, you in some sense divide the system up in subsystems. So in each subsystem you can apply the mean field description that I have talked of before. And then what you need to take care of is the interaction between subsystems. And this is again mediated by the interaction between spins. And the presence of this interaction leads to a gradient square term in the free energy, which describes non-local interactions between the spins. So what we have ended up with, in the end, I will write this on this board because this way I can leave it there and then you can always consider it. In the end, what we have gotten was that the free energy of this heterogeneous system is described by what is called free energy functional. So this is a functional of the magnetization. I will talk about this just in a second, which is given by a volume integral. And then here we have constant k times the gradient of m squared. And as I have shown Okay. So, the subject of study for today is precisely the elements that I have written on the board. Well, not so much the middle line, the Landau polynomial. We have already talked about this a lot yesterday. But it will be about functionals, about functional derivatives, and about the equations that are below. So I will first try to motivate you a little bit more mathematically what these objects are, functional and the functional derivative. And then we'll talk about the properties of this model, and in particular about the existence of interface solutions, surface tension, and then some of the physics that is implied by the existence of such interfaces. Okay, so let's start. So, first of all, the essential object for all phase field model is this Ginzburg-Landau free energy functional. So in our case, it's a free energy, and strictly speaking, I should write it this way. This is the standard notation in mathematics for a functional. So this is a functional. What does a functional mean? A functional is an application from a space, certain functional space. For example, the space of all continuous and differentiable function, L2. So L2. And this goes to the space of real numbers. So in words, what does it mean? The functional takes as an input a function. That is, m is not a variable, it's a function, so the variables are all values of m of x. Okay? So in that sense, you can say that a functional is a function of an infinity of variables, because in some sense the value of m in each space point is a variable, which can be varied independently because it's a field, so you can change it at any space point. So a functional, in that sense, is a function of an infinity of variables, and it goes into the space of real numbers, because the value of the functional is just a number. It's the value of the energy. Okay? So that's the definition of a functional. What we need to define a little bit better is what are variations of this functional, or how we can describe or understand changes in this functional when we change the function. Or rather, let's say, okay, we have a value of the energy that depends on the whole field. If we vary this field somewhere, somehow, how does the energy change? So we need mathematically to define this. Now, to make you feel a little bit why this is non-trivial, or why we have to talk about this, now I will just remind you how the standard derivative is defined. Okay? So if I have a function f of x that it goes from r to r, okay, that takes a real value variable x and gives a real value f of x, okay. You all have seen in your algebra 1 analysis 1 classes how to define the derivative. Derivative f prime of x, how do you define this? Well, you say I take the value if I make a little change in the variable, so I add a little quantity epsilon, I subtract from this the original value, then I divide this by epsilon, and then I take the limit of epsilon going to 0, because in this way I can define a quantity that is independent of epsilon. Okay? So that's the proper mathematical definition of the derivative. Now, if I have this functional, in fact, the functional f depends on the whole function. So the variation is sort of more complicated, because let's say, for simplicity, I will do all this mathematical stuff in one dimension. Okay. say I have here the space coordinate x, and here my function m. So my function m might be any profile. And then I can vary this functional by changing the function. So say I can choose, instead of having my original m of x, to have a new m of x that is sort of different. And this shaded area here I will call delta m, which is in some sense the variation of the function m of x, and so this also will be a function of x. Okay. You also see that if I do this variation in the space of continuous function, strictly speaking, I cannot vary this function in one single point because it has to be continuous, right? So I can do something localized, so I can do a variation that looks like this. It is a little bump, so to speak. So this will approach a delta function, but strictly speaking, I cannot vary this field in a single point. So we will see how to define this. It will induce a few differences with respect to the normal derivative, but you can do everything rigorously, and as we will see, in the end we will define an object that is like if you change this field m just in a single point. Okay, and this will be called the functional derivative. Okay, so this is our goal, to define how we can calculate the variation of the free energy F if we do a variation of this field. Okay. Now for me the simplest way of defining this is actually to make a detour and to consider a discretized version. So I will consider a general functional F, which will be an integral, and I will be slightly more general than this functional here. I will consider that this is a function g of the gradient, and since I'm in one dimension, this is just a derivative with respect to x. And then I will have a function f of m. Okay? So this part depends on the local value of m, and this part depends on the gradient of m. Okay? And as I say, I'm in one dimension, so this is just an integration over x. Now I will consider a discrete version of this. What do I mean by discrete version? Well, I will do like as if I... So I will have n that is L divided by delta x variables. And of course, by this procedure, I go from an infinite number of variables, which would be this here, as I said. Formally, the value in each space point is a separate variable. Here I've simplified the problem because I have a large but finite number of variables. And then what I will write instead of this integral is just its approximation by a Riemann sum. That is, I will sum the value of this function here about each grid point. So what does it give? So f is approximately, now I have the sum of I equals 0 to n minus 1. And then I have here the first part where I will take the gradient, and I will take the gradient in a discretized way. That is, I will have here mi plus 1 minus mi divided by delta x. That's the value of the gradient. And then here I will take just the value of the mi. Okay? So this is an approximation of the value of the integrand. I take the sum, and of course I also need the approximation for the integration element, so I need to put the delta x here. Okay. So this goes back to your elementary analysis classes, but you remember this is a Riemann sum. Okay, now what is the advantage of this? This now is a function of big N variables, and I know how to calculate its derivatives. So I can study what is the difference of when I add now to one of the grid points a little variation epsilon. So I can say I will go from mi to mi plus epsilon. Okay? Which means that I study a particular variation. Thank you very much. I study a particular variation in some sense. So to come back to the previous pictures, here I have m of x. Now I'm in a discretized system, so I have approximated the m of x by its values at the grid points, and what I'm doing now is I'm shifting one of these grid points by an amount epsilon, which means that the variation that I consider is sort of like this. Again, it's a sort of approximation of a delta function. But the advantage is, of course, now I can calculate what is the change in my approximation for f. We all know how to do that. And now I'm going to write this. I'm going to write this here. Okay. So, delta f I define as the difference of f, and I will call this m plus epsilon. It's understood that the epsilon applies only at one grid point, minus f of m. And now you can see what happens. So for example, if I change the value of mi by an amount epsilon, of course here I will have f of mi plus epsilon instead of f of mi, but this I can approximate by a Taylor expansion. So this, the local term, will give me f prime of mi times epsilon. Okay? That's the change that I induce in this term if I switch from mi to mi plus epsilon. Then, where does the mi appear? In addition, you see I have the gradient terms here, but you see that in the gradients, each mi appears twice. Okay? It appears once here in the difference and there in the difference. For example, if I look at M3, M3 appears in M4 minus M3, and it appears in M3 minus M2. Okay? So I have to consider this term here. Once, so when the mi is up front, so I will get a g prime, and here the mi is up front, so I have mi minus 1 divided by delta x. And I also have the inner derivative, which is a delta x here, and I have the epsilon, which comes from the Taylor expansion. That's why I have the derivative here. And then I need to consider the term where mi is here, so this comes with a minus sign from the inner derivative. So here I have mi plus 1 minus mi divided by delta x, epsilon by delta x. Okay? So if I rewrite this, I will start with this term here. So I will have a minus sign, and then I have an epsilon over delta x. And here I have a g prime of mi plus 1 minus mi by delta x minus g prime of mi minus mi minus 1 by delta x. Okay, and then I have a plus f prime of mi. And of course, I have forgotten in all of this that I have also my integration element, so I have a delta x that is outside here. And the same thing here, times delta x. Okay. Now, if you look at this, you can actually give this a quite simple interpretation, because what you have here, you have twice g prime, and you have g prime once taken in some sense at the points I plus 1 minus mi, so you have G prime here. And the other term is G prime just to the left of it. Okay? So you have the difference between two values of G prime at different space points divided by delta x. So this is nothing but the space derivative of G prime. So I can rewrite this approximately. Remember, I've started from a continuum thing, I have discretized, and now I'm going back to the continuum in some sense. So I can write this approximately as delta x times, and now we have minus dx of G prime of dxm. And then I have the plus f prime of m. Yeah, the parentheses should be there. Okay? And I have also forgotten that in all of this I have the epsilon. So the epsilon should be outside here. So remember, the epsilon comes from the fact that I move one grid point by an amount epsilon, so it's logical that this variation should be proportional to epsilon. And as I have said, this is a localized variation of the function m of x, and the width of this variation is proportional to delta x. That's why there is a delta x outside here. So as you can see, I have outside here an epsilon and a delta x, and inside here I have an object now that is independent of my particulars in some sense. So I will define now an object that I will call delta f by delta m of x, which is the limit of epsilon to 0 and of delta x to 0 of what I have just calculated of delta f, and then I have to define by epsilon and by delta x. Okay? So you see that this is a perfect generalization of the ordinary derivative. In the ordinary derivative, you only had the epsilon to 0, which means that you considered infinitesimal variation of the variable. Here I consider at the same time infinitesimal variations of the variable and applied over an infinitesimally small space element in some sense. So it corresponds to the limit where both the thickness and the width of this little surface here go to 0. So that's the mathematical sense of this object. And by our calculation, we have obtained an expression that is, will be minus dx of dg by delta dxm. Okay? Plus f prime of m. Now you have to get used to this somewhat barbarian notation, which you will see in many papers. So don't be afraid. Okay? What does this say? Is actually my integrand in the functional here, that is over there, is actually the function of two variables. One is m and the other is gradient m. Okay? So what this means is nothing but I take the derivative of the integrand with respect to the variable dxm. So dxm is just a variable, you could call it y. So this is the partial derivative of the integrand with respect to the variable, and then I take the space derivative of this. Okay? So if you have followed the calculation that we have done, then there is nothing mysterious to this formula.
Mathis?
Yes?
Is the delta function we say epsilon should go to infinity as delta x goes to 0 so that the area of the curve remains at the same value. But here we are saying epsilon also is going to 0.
Yes.
So what is the
it's
epsilon going to 0 means no variation. I mean,
no. It's not well. You see, I'll come back to this question in a few minutes because it has to do with a problem of dimensions. I will come back to that. Okay. So the thing is. Okay, so this term, where does it come from? It comes from the fact, actually, that when you vary the field in one point, the gradient will be modified on both sides. Will be modified on both sides of the points and in opposite directions. That's where the space derivative comes from, because you modify it upward on one side and downward on the other side. And you have to take the difference of that in order to get the total variation that comes from the gradient term. Okay? So, if we have this, now a few remarks. So first, in 3D, how does this generalize? It's actually quite easy to understand now, because if I do the variations in 3D, well, the local term is not going to change. Okay? And, but the gradient is going to change, because now there are three components of the gradient. So I will have three such terms. So the general definition of this functional derivative delta f by delta m is the following. It's f prime of m minus, and then there is a sum over, say, I equal x, y, and z. And then I have di of dg by dim. Okay, so it's just three such terms according to the directions x, y, and z. And so often you will see this written minus as a divergence, because this is nothing but a divergence. It's the derivative with respect to x of a function of x plus the derivative with respect to y of a function of y. So dg by d m. Okay? And why did I go through this derivation in so much detail? Because if you see this written in a paper, you say, huh? Are these guys nuts? It's true. I mean, because this is absolutely non-standard notations, and even if you show this to a mathematician who doesn't know the field, he say, what is this? Right? So the sense of this is this, and I have motivated why this should be of that thing. So this was remark number one. Now you are equipped for no matter what kind of Ginzburg-Landau functional, you can just apply this formula and you will get the right result. Okay. Sometimes you have to be careful when you apply it, because the dependency might be complicated. We will see on Thursday and Friday a case where this is more complicated than for the standard gradient squared. When we take into account anisotropy of the interface energy, then the calculation of this is a bit tricky, but the formula always applies. Okay. Now this was remark number one. Remark number two comes back to the question of guru. I want to talk somehow about dimensions. So I will leave this here. So df by dm. Okay. So I'm a physicist, so I'm always worried about units. So F is a free energy. So the units of F is energy, so it's joule. Yeah? Now I have just defined, so and I will write F, which is the integral of 1/2 kV of that m plus f of m. Okay? Now I have defined this delta f by delta m. So what's the dimension of delta f by delta m? If I look at this expression, for you, what is the dimension of delta f by delta m? What's the units? No. Okay, maybe it's because you're not very familiar with the magnetization. Remember, the magnetization, as I have defined it yesterday, was just a number. Because it was the average of a spin value that was between +1 and -1. So M has no units. It's just energy? Okay. Everybody agrees? Okay, look at this. What's the unit of F prime? Where does the little f appear? I give you a hint. F appears here. So what's the units of F? Joule per meter, yes, or per. It's rather energy per length to the dimension d, because it appears inside the integral here. So it's a density. It's a free energy density, actually. So the units is joule per meter to the dimension d. So if we are in 3 dimensions, it would be joules per meter cubed. In my one-dimensional example that I had before, it would be joule per meter, right? So you see that the functional derivative here brings in a dimension of length to the power of the dimension. And why is this? Actually, remember what I have said to you. The variation has always to be taken around a certain space point. But, well, if you do a variation in a single space point is what we call in mathematics a set of measure 0. So it doesn't carry any weight, right? So in reality, how can we interpret this? If I want to calculate the real change in F, okay, well, I can take the functional derivative, but then I have to specify 2 things. First, I have to specify by how much I vary the field. And then I have to specify in what volume I vary it. So I have here, in some sense, a delta x to the d. And only then I will get the true variation in energy. So that's the physical sense of this. And now to come back actually to the initial drawing that I had, which I will try to reproduce here. So here I have x and here I have m. So here's the function, and here I have my variation delta m of x. How can I really properly define the variation of f? Well, the total variation of f will be what? It's a generalization of that. I have to specify by how much I vary and where. So the total variation of f will be an integral over delta f by delta m of x times delta m of x dx. And now, since we have introduced the general case, I can also put a vector here. So this is the proper way of defining the variation. Now, coming back to your question with the delta function, you see that if I want to go about this the brutal way, and I say m of x goes to m of x plus delta of x minus x0, well, that's what you would like to do in some sense. You see, that's not as simple as that, because delta is the dimension of 1 over space. So you cannot do that dimensionally. You cannot just add a delta function. You have to add the product of a delta function and the length. Otherwise, it's not properly defined. Right? So this is wrong. And I know this because yesterday evening when I sat down to go through all this again, that's how I first tried to do it, and it doesn't work this way. So here is the proper expression for the total variation of the free energy when you vary the field M. Okay? And so this is really rigorous. You can put here all what you call test functions, what the mathematicians call test functions. So you do any variation of your function m of x and you will get the proper change in the energy that is given by this function. Okay. This is the definition of the variational derivative. Now we can start to do things with it. So let me first come again to this definition of my equation, that is the Allen-Kahn equation. So I have written down u delta the ETM equal to minus a constant times delta F by delta M. Now, what's the motivation of this expression? I have already mentioned it in some sense yesterday. We know that the free energy is the thermodynamic potential, and so the proper thermodynamic evolution should always decrease the free energy. So let us very quickly prove that this dynamics always makes the free energy decrease. It's very easy. Well, I will calculate the total time derivative of the free energy. Okay? But now, since we have this expression, I know how to do that, because the variation in time is just a particular case of a variation of the free energy. So I can plug this in for the variation of df. So I have to calculate the integral of the functional derivative over dm of x. And then I have to put my variation, but this variation is now just dm of x by dt. Because I consider a time variation, and then I have to integrate over x. Now you see, if I plug in this expression for dm, I will get that this is minus gamma times the integral of delta f over delta m of x squared dx. And you can see this is the integral of a square, so the integral is always positive. Since there's the minus sign, this is always smaller or equal to 0. So, by this two-line proof, you can show that this equation makes properly the free energy decrease, and therefore will drive the system to a thermodynamic equilibrium state. The thermodynamic equilibrium state is one where the variation of the free energy is 0. Now just a few words concerning mathematics. What we actually have done here is just the generalization of, say, if you have a particle in a potential, V of x, and what you do is, well, you say that the particle experiences a force. The force is minus dB by dx. And then the particle follows this force. Okay? Here we are just doing the same thing. The variation of the free energy, the variation, the derivative in some sense, is just the equivalent of the force. So it's the same thing as here. Your particle is resting in the potential, and in the same sense your field has a current configuration. If the derivative is non-zero, that means that there is a force acting on the field. And this equation is just saying that the field follows the force. So it's just the same thing as having the little point particle going down in the potential. Okay? So in that sense, this is just the same physics as going down the gradient, and this is why mathematicians call this the gradient flow. So they call it the gradient flow dynamics, which means that you are following the natural force, and since you are doing that, this is very intuitive. It's just like if you follow with your particle the force, it will always go down in the potential. There's a perfect analogy. If you do this dynamics, your field will always go down in the thermodynamic potential. Okay. So this is said. We have defined the variational derivative. We have found that this equation properly drives the system towards an equilibrium state. So next is, we will study that equilibrium state. So, let's come back to our Ginsburg-Landau free energy and apply what we have just learned in some sense. So, I will take this expression there, and I will again go in one dimension to simplify the notations. So I have my f of m, which is integral of 1/2 k dxm squared plus f of m. Well, the f is written there, and I'm not going to spell it out for now. So let's calculate what's the functional derivative. Let's apply our formula. So we have first the gradient term, we have a minus, and then I need to derive the integrand with respect to dxm. So this will give me k dxm. That 1/2 will go away with the derivative, the outer derivative of the square. And then I have to take the divergence of this whole thing. And the other term is easy, which I have just f prime of m. So in total, what I will get is minus k dxxm plus f prime of m. Just to mention, if I'm in 3 dimensions, in fact, you remember that there is a sum over the 3 directions. So instead of getting just dxx, I will get dxx plus dyy plus dzz. So in 3D, this will give minus k Laplacian of m. Right? So you can remember this as a special case of this functional derivative. The functional derivative of a gradient squared gives a Laplacian. Okay, so this is the functional derivative of our particular Ginsburg-Landau system. Let's study equilibrium. Equilibrium, as I said, is when this variational derivative is equal to 0. So let's write it out. 0 must be equal to minus k dxxm plus f prime of m. Now, what are the equilibrium solutions of this? Now I need to maybe go back a little bit. I'll put it here. I'll put it up here. Remember that we are going to speak about a system below the magnetic phase transition, that is, I'm interested in the case where this potential has the double bell shape. Okay, so the question is, what are the equilibrium solutions of this? Now, of course, there's two that are almost trivial, because, of course, this potential has several points where f prime is equal to 0, that are the two minima and the maximum. So, of course, if I'm at one of these points, and if my field is just constant, that's an equilibrium solution. Okay? So, I call this M0. So if I have M is identical to plus or minus M0, that's okay. That's a stable equilibrium solution. Why do I say stable? Well, it's kind of obvious from the plot. If I move any space point away from this value, the potential will go up, so the point will be brought back to its original value. Then, if I have m equal to 0 everywhere, formally that's also a solution of that equation, but it's clear that this one is unstable because I'm sitting here, so if I do a variation, this will make the energy decrease, and so the system will be driven away from that state. So, this is unstable. But now, the most interesting ones are actually the inhomogeneous cases. Well, as I said, we will be interested in domain patterns, so not surprisingly, our main interest will be in solutions that are not homogeneous, because these two solutions correspond to the plus and minus domains in some sense. But there is a third type of solution, in fact, which is the interface solution, which in some sense starts out here and goes over the top to the other one. Okay? That is, we are looking for solutions that are non-homogeneous, so that have as a boundary condition minus m naught on one side and plus m naught on the other side. Okay? That's the mathematical formulation of what I have said. We want to find solutions where on one side it's minus m0 and on the other side it's plus m0. Okay? So, for this, let me do a few preliminary steps, because this will make things easier. Now I have to come back to this potential. Okay, so my potential, actually I see that here I have put two normalization factors. I have put 1/2 here and 1/4 here, but that doesn't make a difference. That's just a convention about how to define A and B. People often do that because this way the derivative is easier. So let me tell you what I'm going to do. I want to simplify this potential to get rid of the constants A and B in order to have simpler notations. So I'm going to rescale these equations. So I'm going to go to a variable where I divide this magnetization by the equilibrium value in such a way that the function goes from -1 to +1, just to simplify things. Okay? So I'm going to calculate the equilibrium magnetization. So I have that f prime must be equal to 0. So what do I get? So I get A t minus tc times m plus d m cubed. So remember that I'm below the critical temperature, so what I get is that m star, m0, m star, here I call it m star, so let's say m star, squared, I can express as a over b times Tc minus T. So if I'm below the critical temperature, this is positive, so I get solutions. Okay? And now I will introduce the variable m tilde, which is m by m star. So of course, I have that m is equal to m tilde times m star. And so what I get is if I rewrite this function in terms of m tilde, I will find that this is a times t minus tc squared divided by b, and here I will have minus m tilde by 2 squared plus m tilde 4. And precisely to simplify notations, I will call this whole prefactor, I will call big H minus m tilde squared by 2 plus m tilde 4 by 4. Okay, then I will also define, I will redefine this gradient coefficient k, because if I replace m by m tilde, I will have an m star that comes, so I will also define a k tilde, which is equal to k times m star. Now, what do I have gained by doing this? It's an elementary procedure. You will see that I have simplified my notations for the functional. So now my functional will read 1/2 k tilde grad m tilde. I will go to one dimension. I had set for dx m tilde squared plus h minus m tilde by 2 plus m tilde squared. So instead of having this sort of complicated polynomial, now I have only two constants here, k and h. Then of course I forget all the tildes, okay? That's what the physicists then always do. So I have f is equal to 1/2 k, but which is redefined dxm squared plus h minus m squared by 2 plus m4 by 4. And now if I come back to my interface equilibrium, you will see that the equation has simplified quite a lot. So I have a 0, which is minus k dxxm, and then here I have a plus m3 minus m, probably. Yes.
H.
Ah, yes. Important. Plus h. Okay. And I can do one more step. I can divide through by h. So here I have k by h dxxm plus m3 minus m. Yes.
And zero means one phase, a stable configuration means one phase, and unstable means another phase.
No. You see, here in this potential there are 3 stationary points. 2 minima and 1 maximum. Okay? The stable phases correspond to the 2 minima. So these are the domains with upward pointing magnetization and downward pointing magnetization. Okay? This third stationary point you will never see because it's an unstable point, so in no natural system you can realize it, because there will always be some microscopic fluctuations, and as soon as you take it away from that point, it will go either here or there. So there are 2 stable phases, and these 2 stable phases now in terms of this m correspond to m equal +1 and -1, upward and downward. So here m equals 0 is an unstable solution. Okay. So this is the equation, and now we would like precisely to find a solution that links the 2 stable phases. Now it so happens that for this polynomial here, there is an exact interface solution to this equation, which I will very rapidly demonstrate to you. Anybody knows this equation? Anybody has seen it? Anybody can guess what the solution is? Well, I admit that it's hard to guess. It's a non-trivial solution and a non-trivial equation. So, of course, I also read it in the literature. I didn't guess it. So I will give it to you. The solution of this equation is a hyperbolic tangent. So let's try it out. I will just demonstrate to you that it works. Okay? So if I put m of x, which is equal to hyperbolic tangent of x by psi, I call this psi. So psi is a length scale. I will come back to this in a moment. And so let's see whether this works. So we will have to calculate the second derivative. So I will start by calculating the first derivative. So of course there is the outer derivative, which is hyperbolic tangent prime, and then there is the inner derivative, which is just 1 by psi. And so what is hyperbolic tangent primes? Who remembers the hyperbolic functions? Who remembers the trigonometric function? What's the derivative of the tangent, the ordinary tangent? Huh? Yes, minus cosec squared. Is it minus? I think it's plus. Anyway, the derivative of the hyperbolic tangent is 1 by cosine hyperbolicus squared, x over psi. And so this is the equivalent of the cosecants, 1 by cosine. So now you have to remember something about your hyperbolic functions. I can rewrite this 1, which in ordinary trigonometric function is sine squared plus cos squared. 1 in the hyperbolic function is ch squared minus sh squared. Ch squared. So this is just special function knowledge. So what you get is that this is 1 over psi, 1 minus ph squared. And why do I rewrite this in this way? Because now it's easy to calculate the second derivative. Because dxxm is just one more derivative of this. And since I've already calculated the derivative of the hyperbolic tangent, now I can just apply. So I have the 1 over psi, and I will take the outer derivative, which will bring me in a minus and a squared and another 1 over psi. So I have minus 2 over psi. The outer derivative also brings me 1 hyperbolic tangent, and then I will just apply that th prime is 1 minus th squared, which is the same that I have just calculated. So in total, I have that this gives me 2 over psi squared, th3 minus th. So you see that we have the essential much. The second derivative is equal to the cube minus the linear, which is exactly what we have here. We have the second derivative, the cube, and the linear. So all we have to do to match this solution is to find the good value of psi. Okay. So we have that. Let's see. So if I rewrite this equation, it's k by h exxm is equal to m3 minus m. So if I compare the two, this works if, now let's see, the inverse here, if psi squared by 2 is equal to k by h. Okay, you see I multiply here and I get the same expression, so the two constants need to be the same. Or in other words, I need that, is it the right way? Yes. I need that psi is equal to square root of 2 times square root of k by h. Okay? So finally, the final solution is m of x is equal to hyperbolic tangent of x divided by square root of 2 square root of k by h. Okay, I will write this out. Okay, I think this is a good point to have a break because the first hour is over and we'll continue after 15 minutes from now.
So coffee is there outside?
One thing that I forgot, namely, I mean, of course, probably you all know how the hyperbolic tangent looks like, but still I want you to draw it. So here is m as a function of x. So how does this solution look like when it starts out, say, at -1, and it goes to +1? So you see that it has exactly the structure of an interface. Here's one of the stable phase, so this is the downward pointing phase. Here's the other stable phase, this is the upward pointing phase. And here we have this interfacial region, okay, where the order parameter goes in between its two equilibrium values. And this region has a characteristic thickness, okay, which I call psi, and which is given for this particular potential by this value square root of 2 square root of k by h. So we are going to study this in a little bit more detail. And the first thing that I want to do is I have calculated explicitly this interface solution for the potential that I have written down here. That is called the fourth order potential because it has a square in the fourth order term. The first thing I want to do is to show you that such an interface solution is not limited to this exact potential, but that an interface solution exists for any double well potential. Okay? And for that I will introduce a tool that will also be useful for the following developments, which Tim Langer in his article that I have given in the reference list calls the mechanical analog. Okay, so what is this? So let me give you a small variation of the free energy functional that we always study. So we have the 1/2 k grad m squared, but then I had sort of rescaled this fourth order polynomial, so I had a constant, and the remaining function was just minus m squared by 2 plus m4 by 4. So let me keep the h, which is a physical constant, and let me put here a function, fw, which is just a double well potential. So fw has the shape of a double well, and now this is a dimensionless function. Okay? And then, of course, the interface equation, it just becomes k dxxm is equal to h f prime w. Oh wait, in my notations here actually, okay. Okay, sorry, let me come back because in my notes I have done things differently, and if I switch now, I'm in the danger of mixing up some things. So I will call Fw the double well potential, and Fw will be of the form of this constant h times some dimensionless function. Anyway, and so there is no h here, it's the derivative of the potential. So you see that this is an equation which I have to solve. So I have shown you for the particular case of this potential, there exists a solution. Now in order to make you understand that for any double well potential there exists a solution, I will just make a little sort of magic trick, and I will explain you what it means. I will just change notation here. I will call x t, I will call m x, and I will call big K small m. So you may ask, why is he doing that? Okay, let me rewrite this equation. With these new notations, m dtt x is equal to f prime w. Does this equation remind you something? What does it remind you? Looks like Newton's equation, right? It will even look more so if I write m dtt x is equal to minus dv by dx, and you can understand this is, if I write, this is df by dm. Okay, so no, yes. Originally, this f prime means a derivation of this potential with respect to m. So m becomes x, so this becomes a derivation with respect to x. I've just renamed fw to minus v. So I will complete fw becomes minus v. Why do I do that? Because this is the equation for a particle in a potential. Okay? And the potential is actually the negative of the double well potential. So if I draw this, so this is v as a function of x. The potential will look like this. So this interface equation is perfectly equivalent to the equation of a particle that moves in that potential. And now you can see, since these two maxima now are exactly at the same height, there's always a solution where I put the particle on this hill and I give it a very slight start. It will roll down here, it will go down through the well, and it will come up again, and it will exactly come to rest on the other hill. Why is that? Because the energy of these two hills, the potential energy is exactly the same, and there is no friction in this equation. Right? So this is Newton's equation, and it's the equation of a conserved system. So the total energy will be conserved. That means if I start at a certain height here, I can come back to exactly the same height. Okay? Now, why is this useful? It's useful because it gives an intuitive meaning to a few relations that will be extremely useful. Okay? So, for example, what? First of all, for a particle in a potential, you know that there is energy conservation. So the total energy, which means the kinetic energy plus the potential energy, is a constant. Okay? Well, the kinetic energy is what? Is 1/2 mx dot squared. 1/2 mv squared. The potential energy that was invested, what? This is the equilibrium value of the potential. So here we have V equilibrium minus V of x. Or let me say, yes, plus V of x. So this is the total energy, this is the kinetic energy, this is the potential energy. And this must be equal to a constant, and we know that constant because at equilibrium, where we started from, there was no kinetic energy because the velocity was 0 and the particle was at that potential, so it's the equilibrium. And from this, it follows what I had written before. There is 1/2 mx dot squared is equal to V equilibrium minus V of x. So, from this, if we translate this back into the language of the phase field, I just need to put my notations, I revert my notations backward. You see here I have 1/2 m was the gradient constant k, x dot was dxm squared is equal to, and here I had that the f of m, fw of m minus fw of m equilibrium. We will need this in the following, and because there is this mechanical analog, and this describes the conservation of energy, and you see that the kinetic energy is sort of equal to the potential energy. This is sometimes called the equipartition equation or relation. Let's put it relation.